Hi, my name is Gabe. I'm a mathematician and a tutor, and I'm excited to dive into some statistics with you. Today we are going to introduce the concept of conditional probability and one of its most important results, Bayes' theorem. This video will start by introducing the concept of and the formulas for conditional probability. Then we will see how conditional probability leads us to Bayes' theorem. Finally, we will see Bayes' theorem and conditional probability in action in an example. Let's get started. First, we need to think about why we need conditional probability. In basic probability problems, we often talk about independent events. If you were to first flip a coin and then roll a die, the two events would have nothing to do with each other. The result of the coin flip would not impact the roll, while the roll would also not affect the coin flip. When events cannot influence each other, we refer to them as independent. Not all events, of course, are like this. And this is why we need to talk about conditional probabilities. Conditional probabilities allow us to talk about related events. Let's look at a basic example. If you are planning on going to the park, you may well check what the weather is before you go. If it is sunny, you will probably go. If, on the other hand, it is rainy, you might not. Neither is a guarantee. You might like to go on certain rainy days or be tired on very sunny days, but the weather conditions the likelihood to go to the park. Let's put this in mathematical terms. Given two events A and B, we want to know about the probability of event A happening given that B has already occurred. We write this statement as P A bar B, or the probability of A given B. This probability is equal to the probability that event A and event B occur, divided by the probability that event B occurs. It is important to think about why the probability of B, the conditioning event, is in the denominator. This is because we are calculating the probability that A happens given that B has already occurred. Placing the probability of B in the denominator tells us that we are only focusing on the times when B has already happened. Importantly, we can also reverse this formula. That is, we can say that the probability of B occurring, given that A occurs, is equal to the probability that A and B occur divided by the probability of A occurring. Notice how, in both of these equations, the conditional event, i.e. the given event, is in the denominator. Let's see how this applies to our park example. Let's call going to the park event A, and staying home is the complement or opposite of going to the park, so we call it event A prime. Similarly, we say that the sunny day is event B, while a rainy day is event B prime. From here, let's say that you go to the park about 40% of the time overall. That means that the probability of event A is 0.4. Then we have that is sunny 50% of the time, giving us that the probability of B is 0.5. Finally, let's say that it is a sunny day and you are at the park 35% of the time. This means that the probability of A and B occurring is 0.35. Now we can begin to ask how likely it is that you are going to go to the park given that it is sunny. That is, what is the probability of A given B? Well, let's take the information that we have and think about what equation we have to use. Pause the video for a second to see if you can select the proper form of the conditional probability formula. Welcome back from that little break. Since our equation is conditioned on B, we need to have the probability of B in the denominator. Therefore, PA given B is equal to the probability of A and B divided by the probability of B. Plugging in our values, we find that PA given B is equal to 0.35 divided by 0.5. This tells us that the probability that you go to the park given that it is sunny is equal to 0.7, or 70%. This makes sense as you are generally more likely to go to the park in the sun, and thus the conditional probability is different than the basic probability of going to the park. Now, this worked because we had information about the likelihood of A and B occurring at the same time. Sometimes, however, this doesn't happen. For example, while we may sometimes be able to figure out the conditional probability of going to the park based on the weather, can we tell something about the weather given that we are either at home or at the park? This is the question that Bayes' theorem is designed to answer. Bayes' theorem is an incredibly powerful tool because it describes the relationship between the two directions of a conditional probability. Crucially, with it, we do not have to know anything about the probability of event A and B occurring, which is often difficult to know. Let's see how we state Bayes' theorem mathematically. Given two events A and B, Bayes' theorem tells us that the conditional probability of A given B is equal to the probability of B given A multiplied by the probability of A, all divided by the probability of B. This equation can be really hard to remember, so let's break it down. First, notice how the conditional probabilities switch orders between the left and right side of the equations. This represents the fact that Bayes' theorem relates the two possible conditional relationships between events. Second, recall that this is still a formula for conditional probability. Because of that, the probability of the conditioning event, in this case B, is in the denominator of the formula. If you can keep track of these 2 points, it should be much easier to remember this formula. Let's see how this works with our example in the park. Recall that we know that the probability of going to the park is 0.4, and the probability of it being sunny is 0.5. We also calculated that the probability of you going to the park, given that it is sunny, is equal to 0.7. This only tells us about the effect of the sun on going to the park. What if instead you wanted to know about the likelihood that it is sunny, given that you made it to the park? In this case, we are going to use Bayes' theorem to calculate the probability of B given A, making sure to switch the order of our conditional probability and keeping the conditioning event in the denominator. Our version of Bayes' theorem here reads as the probability of A given B times the probability of B, all divided by the probability of A. Plugging in our values, we have 0.7 times 0.5, all divided by 0.4. If we calculate this out, we find that the probability of it being sunny, given that we are in the park, is equal to 87.5%. What these results tell us is that there is actually a stronger relationship between you being in the park and it being sunny than there is between it being sunny and you deciding to go to the park. These directional relationships are at the heart of Bayes' theorem. Other applications of Bayes' theorem rely on more complicated calculations of individual probabilities or inputs to the equation, but this is the fundamental intuition behind the calculations. Bayes' theorem is at the heart of many important statistical testing procedures and real-world applications. Medical tests are known to have probabilities of false positives, that is, a positive result conditional on someone not having a disease, and false negatives, a negative result conditional on someone having a disease. Using Bayes' theorem to evaluate test results and potentially retest certain patients saves unknown numbers of lives every year. Meanwhile, manufacturing processes are known to create occasionally faulty products. If the acceptable failure rate of a process is known, careful testing of a subset of products can alert manufacturers to additional problems. Without Bayes' theorem, these tests would take longer and would not be able to pinpoint flaws in processes as accurately. In general, real-world events are rarely independent. If we want to understand the relationships between complex events, we need to make use of conditional probabilities and Bayes' theorem. We started today's lesson by exploring how conditional probability allows us to talk about related events. We then realized that it is sometimes important to be able to reverse the direction of our conditional probability calculations. To do this, we introduced Bayes' theorem, which relates the two possible directions of conditional probability. Finally, throughout this lesson, we practice using these concepts on a basic example. We further mention some fields where Bayes' theorem is used every day. Hopefully this has been a helpful introduction to the concepts of conditional probability and Bayes' theorem. You may encounter some more complicated problems with these concepts, but the basic principles will always be the same. Feel free to explore more areas like this on Chegg.